All right. Can the online guys see the screen clearly? Can you tell me?
Yes, sir, we
Gentlemen,
can see
on.
the screen.
Very good. I think you can go and rest in peace for some time. If I need anything, I will message you. Thank you, man. All right. We talked about the derivation of Bernoulli equation in the last class on, this one. From this topic, this one only. And in the first topic, I have shown you a couple of them as possible derivations. So one is, the relationship for the coefficient of dynamic viscosity, that which I worked out. I will upload these solved versions. Then also the calculation of viscosity using a viscometer, that derivation, and the calculation of the internal pressure in a bubble or a soap, bubble, air bubble or soap bubble. The difference is the soap bubble has a certain thickness for the film. It will have 2 times the circular periphery length. And then a derivation on the capillary rise in a tube, in a capillary. So these are simpler. So these four are possible derivations that I might ask in that lesson. And in this one, only Bernoulli equation. And in the next chapter, which is the last chapter for us, which is heat transfer, there is only one equation that you will be getting, Q equal to minus K A dt over dx, which is the Fourier heat conduction equation. So we just discussed that. It is not a big derivation in itself, but it's just a theoretical concept as derived by Fourier. We'll see that in the next week. From the second topic that I did, which is fluid statics, the pressure acting on a plate that is submerged, a general equation for the pressure, which I will show again today. I will derive it in while solving the exercises. That is another derivation possible. So in total, there are 4 plus 1 plus 1, total 6 derivations that you can have a closer look at. That is the fundamental principles that are applied to these cases, which could be a possible, points of learning. That's why these 6 you can practice. One of them could be there, or none of them could be there, but one of them could be there. This is all right in the exam. What I mean is, okay, practice only those 6. The rest is all equations and formulae sheet, etc. I have also uploaded the formula sheet into Canvas. You will find it in the assessments, the model assessment in thermofluids. I have not put the model exam question paper yet. I did halfway through because of time limitations. I could not complete that. I will do that by tomorrow and I will upload the model exam. So I'm taking some of these problems as exemplar problems because that's the kind of problems you will see. So I will show that. I will put all of that together by tomorrow, and you will see. But this is the formula sheet. It looks a bit too much and too cluttery, but that is what it is. And why it is not allowing me to see this? We will see that. That's the formula sheet. You can just have a look at it. So we'll just be using this, refer to this often when we are solving problems today. Okay. All right. Where are we? Okay, that we have solved some problems in this already. And as I said, the conceptual problems, I will not be writing the answers here. You need to write your answers. If you miss it, you need to watch the video. All the answers are available there. And beyond that, yes, I will be solving all the numerical problems. at least most of them, so that you can solve any of them. So where are we? 12, 12C. I think I solved that for you and explain how and why a siphon works. We talked about this in the class yesterday. As long as the height of the free surface of the liquid in the tank to the free surface of the point where it is delivered, if this is lower than that, the head difference is higher. And therefore, there will be the siphon working. However, the height to which this pipe goes above the surface level, there is a certain limitation to it. That limitation is it can go up to the point, because as you go higher and higher for this bent pipe, the pressure at the top point will be lower and lower. And if that pressure for the given conditions, that is, if it is sea level and atmospheric, normal atmospheric pressure is acting at sea level, and at that place, the maximum height to which you can go with a siphon is theoretically 10 meters, because beyond that, they say the pressure at the top point will be so low, it will be less than the saturation vapor pressure, and where the water will start evaporating and starts forming bubbles there, breaking the liquid column. And so the siphon doesn't work beyond that height. Under normal circumstances, even below that height, it might not work, because the pressure, not only the pressure, there will be friction losses along that length. For 10-meter height, just imagine what kind of friction losses will be there in the pipe. And so they may cause also problems. But theoretically, at sea level, you can use a siphon up to a maximum height of 10 meters. And so in this problem, he's saying cold water at 7-meter height, there is still possibility it may work. It is feasible, because it is less than that the 10-meter threshold height that is given for siphons based on the limitation of getting vaporization. A student siphons water over an 8-meter high wall at sea level, acceptable. She then climbs to the summit of Mount Shasta. I don't know where it is. Um, Elevation 4,390 meters. The atmospheric pressure is almost half, because normal atmospheric pressure at sea level is 101 kilopascals. This is 58, and attempts the same experiment. Comment on her prospects for success. So generally, if at sea level it is 10 meters high, if the pressure is reduced to 58 kilopascals, the height also will be almost halved. And so if she is trying to siphon at an 8.5 meter height, whereas the maximum elevation that is allowed for her before cavitation is only around 5.5 meters, so this is not a successful experiment. Probably it won't work there. That is our answer. In a hydroelectric power plant, water enters the turbine nozzle at 800 kilopascals absolute with a low velocity. If the nozzle outlets are exposed to atmospheric pressure at 100 kilopascals, determine the maximum velocity to which water can be accelerated by the nozzles before striking the turbine blades. So this is a case for Bernoulli equation. Let me put it like this. Let's hope I don't disturb any of this. Is it all still working? Okay. So we are using a nozzle here. Uh, Let me, how do I, yeah. A nozzle is delivering water to a turbine. And at the entry, let's say this is point one, our reference point one, and this is our reference point two. And 800 kilopascals is the pressure at the entry, and at the exit 100 kilopascals. We can apply Bernoulli's equation between points 1 and 2. So if you do that, it is P1 over rho g plus V1 squared over 2g plus Z1. So we are using the elevation, the head model, P2 over rho g plus V2 squared over 2g plus Z2. Because 1 and 2 are on the same line, Z1, Z2 are the same, so we can get rid of them. And with low velocity, water is entering here. We can neglect that velocity because no information is given. There is nothing much we can do other than neglecting. And so from this, we can say V2 squared over 2g is equal to P1 minus P2 over rho times g. So we can cancel that g on either side, and we can say, therefore, V2 is equal to square root of 2 times P1 minus P2 divided by rho. G is cancelled because it's equally on either side. So substitute what are the given conditions. Therefore, V2 equal to under root 2 times P1 is 800 kilopascals minus 1000, 100. But this is kilopascals. It doesn't work very well with the rest of the units. You need to convert that into Newton per meter square. So which is times 10 cube pascals, which is Newton per meter square, divided by rho is water density. Whether I state it in the problem or not, you under normal circumstances, you take it as 1000. When you solve it, we get the velocity at the exit of the nozzle as equal to 37.4166 meter per second. So that is the exit velocity. And so Bernoulli equation, what you need to see is what is the data given and how do I efficiently use the Bernoulli equation. And also there are 3 forms of this equation. You may have to choose an appropriate form that is suitable for that application, that problem, depending on the data that is given. All right. Yeah, that is the answer for that. Do you want to ask me any questions or can we move on? All good. A pitot tube static probe is used to measure the speed of an aircraft flying at 3000 meters. If the differential pressure reading is 3 kilopascals, determine the speed of the aircraft. So pitot tubes are used on airplanes on the front side to measure their velocities, and sometimes they are also connected to, the smart computational system that will make automatic adjustments based on the velocity and things like that. And I saw one of the air disasters, something wrong in the pitot tube actually caused the plane to come down. And it's a small device, negligible, but they can cause significant dangers if not properly maintained. It is being blocked, the passage, and so the reading was wrongly. The instrumentation was wrongly reading the velocity and was making wrong automated adjustments, and that was actually causing problem for them. I don't know whether they all died or not, but okay. Okay. The pitot tubes that are used on airplanes are more advanced than a simple bent L-shaped pipe. So they have an internal cavity like this. It looks like this. So there is an internal hole through which fluid is passing. In this case, it could be air. And also in the outer skin, there are two, piezometers attached. They are just simple holes like this. There is a hole here and there is a hole there. And these two are connected like this, which will give you the P static pressure. We saw a tube and just a vertical pipe attached. It measures the static pressure in the flow. That is P static. And this stagnation pressure here, that is measured by connecting this to a gauge. So this is the P stagnation. The stagnation pressure is the total pressure at that point, and stagnation pressure is equal to the static pressure plus the kinetic pressure, which is V squared over 2G. So from this, density of air, so if that data is not given in the problem, don't worry. In the exam, if I give this problem, I will provide you with this data. You don't need to remember this. 0.909 kilogram per meter cube at an elevation of 3000 meter. This is data given. And let's say this is 0.1 and this is 0.2. P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus Z2. Z1 and Z2 are the same for those 2 points. And so we are left with P1, P2. So V1 squared and V2 squared is 0 because that is a stagnant point. That is where the fluid, the air that is moving at high velocities comes and hits the front end nose of the pitot tube and comes to 0 velocity. So that is 0. So from this, V1 squared over 2g is equal to P2 over rho g minus P1 over rho g, which is equal to P2 minus P1 over rho g. So from this, V1 is equal to square root of 2 times P2 minus P1 over rho. And that P2 minus P1 is the difference in the stagnation and static pressures. That's the kinematic or kinetic pressure or dynamic pressure. So that P2 minus P1 is measured by the two pressure gauges attached to the two channels of that pitot tube, and that the difference is given as 3 kilopascals, P2 minus P1. So we can substitute that is equal to root 2 times 3 kilopascals, which is 3 times 10 power 3 pascals divided by the density of air is 0.909. So from this, that velocity of the air which is hitting the nose of the plane is also equal to the velocity of the plane, isn't it? At that velocity, at that elevation, we can't expect cyclonic winds having high velocities. It's almost stagnant wind, and the plane velocity is reflected in the velocity of the air. That velocity is 81.24. So that meter per second is a little bit confusing in the case of an airplane. If you convert that into kilometers per hour, this is equal to 292.48 kilometer per hour. That is the story of this pitot tube attached to the nose of an airplane. Is it okay? So at the end of the day, you can see it is coming down to somehow formulating a condition to apply the Bernoulli equation. There are lots of assumptions here, but given those assumptions and the errors that are creeping in, this is a very reasonable solution. All right. The air velocity in the duct of a heating system is to be measured by a pitot-static tube inserted into the duct parallel to the flow. If the differential height between the water columns connected to the two outlets of the probe is 3.2 centimeters, determine the flow velocity and the pressure rise at the tip of the probe. The air temperature and pressure in the duct are 45 degrees Celsius and 98 kilopascals respectively. Again, this is a very similar problem to the previous one. We apply the Bernoulli equation in a similar way, and only thing that is not known here is at for those conditions, rho of air is 1.074 kilogram per meter cube. You take that and use the same equation, you will get V1 as equal to 24.1781 meter per second. Because it's very similar to the previous one, I'm leaving with you to explore and experience and solve this problem. Exactly similar to the previous one. All right. Can we move on? A piezometer and a pitot tube are tapped into a 4 centimeter diameter horizontal water pipe. And the heights of the water columns are measured to be 26 centimeter in the piezometer and 35 centimeter in the pitot tube, both measured from the top surface of the pipe. Determine the velocity at the center of the pipe. Let us solve this problem. Let's say this is the pipe you're talking about. So what you do for a piezometer is you just create a gap there. Oh, not good, man. Okay. For a piezometer maybe, we just attach a tube vertically there. And for a pitot tube, we just add that pitot tube here. Like that. And your water that is flowing in the tube, here it will rise to some height. That is the P static at the center here. And it will rise to a different height here. That is the P static plus V squared over 2G, the kinetic or the pressure due to the velocity. We take, say, this as 0.1. And this point as 0.2. If you apply the Bernoulli equation between these two, P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus Z2. Z1 and Z2 are the same because we are measuring on the same center line. The velocity at point 2 is 0 because it's the stagnation point. So V2 squared over 2g is 0. So from the remaining terms, we can again write V1 squared over 2g is equal to P2 minus P1 over rho g. Again, g can be cancelled. So we can write V1 is square root of 2 times P2 minus P1 over rho. And what is the data that we are given with? P2 minus P1 is equal to the difference in the height of the two columns here. And that is the static pressure. And that whole thing is the stagnation pressure. P2 minus P1 is the pressure equivalent to that length of the liquid column. All right. Now it is a 4 centimeter diameter horizontal uh, water pipe. That's okay. And the height through which it has risen is 35 centimeters. Therefore, the pressure difference P2 minus P1, because this height is actually representing the whole of it from the center, it is P2, and this is P1 from the center because that distance is the same. P2 minus P1 is this height is equal to rho times g times the height of that column. So rho times, okay, the density is the density of water here, 1000 times g 9.81 times. In the problem, he gave you a 26 centimeter rise and a 35 centimeter rise. The difference is 35 minus 26. But we don't like centimeters to go into that because the rest of them are in meters. You need to divide this by 100 to convert them into meters. So from this, P2 minus P1 is equal to 882.9 Newton per meter square. And if I substitute that here, therefore V1 is equal to under root 2 times 882.9 divided by density, which is 1000. So the velocity of flow is equal to 1.3288. All right. Can we move on? An airplane is flying at an altitude 10,500 meters. Determine the gauge pressure at the stagnation point on the nose of the plane if the speed of the plane is 450 kilometers per hour. How would you solve this problem if the speed were 1050 kilometer per hour? And explain. Okay, so what is given is, let's say, an airplane is moving and air is coming and hitting it. Okay, let's take this point as 2 and a point up ahead as point 1. All right. The density of air, if it is not given at that elevation, is equal to 0.3885 kilogram per meter cube at that altitude. It's a data given in the problem. Okay. Again, using Bernoulli, P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus Z2. As you can see, Z1, Z2 are the same. We can remove that. And the air comes to a stagnation at point 2. So let's take that velocity as 0. And from here, again, our V1 squared over 2g is equal to P2 over rho g minus P1 over rho times g. So cancelling that g again, V1 squared over 2 is equal to P2 minus P1 over rho. Or can we write P2 is equal to rho is multiplied on the other side, P1 plus rho V1 squared over 2. But P1 is nothing but the atmospheric pressure there, isn't it? Therefore, P2 is equal to P atmospheric plus rho times V1 squared over 2. But you know the difference between absolute pressure and gauge pressure. Absolute pressure is atmospheric pressure plus additional pressure, total pressure. But gauge pressure is only the pressure above the atmospheric pressure. That's what we call as gauge pressure. Therefore, P gauge is equal to, it is just the additional pressure over and above the atmospheric pressure. So we don't write atmospheric pressure in gauge pressure. So rho V1 squared over 2, which is equal to 0.3885 times. What is the velocity here? V1 is given, the plane is moving with a velocity of 450 kilometers per hour. When you convert that into meter per second, you multiply it with 1,000 and divide it by 60 times 60. That gives you a speed of 12.5 meter per second. Oh, no, 125. Whatever you say, sir. Once you said that, there is no question asked. Yep. 125 squared over 2. So therefore, the gauge pressure. So this gauge spelling is a bit strange. Sometimes it is written as GAGE and GAUGE. So both are equally valid. One is probably British and the other one is American. 3035.1563 Pascal. All right, that's the pressure. Now the second part of the question is, at V1 equal to 1050 kilometers per hour, that is part B, V1 equal to 1050 kilometers per hour, V1 becomes equal to 292 meter per second. 292 meter per second is way above than 125 meter per second. We need to check one fundamental point here, that is the Mach number. So the Mach number is defined as the actual speed divided by the speed of sound, 340. This is giving a Mach number of 0.8588. Does it ring any bell? Does it ring any bell? Yes, it should ring a bell, because one of the limitations of Bernoulli equation we discussed was, in the case of gases, it can only be applied when the Mach number is below 0.3, because they become compressible beyond a Mach number of 0.3. And so this gas at this air at 0.8588 Mach number is way above the limit at which Bernoulli equation can be applied. So if that is the case, we can't apply Bernoulli equation. If you can't apply, you can't solve the problem. And so that is beyond our limit. Sorry, it's impossible within the limits of the knowledge that we have at the moment. So we can't solve that. Leave it there. Any question? So let me just check the online. Anything happening, guys? Online, are you still there?
Yeah,
Anybody can?
Thank you,
Yep.
sir.
Did you say something?
Oh, I was just saying it's all good. Thank you.
Thank you. Jesse Kilkelly Monroe. Yep. Is it? Is it also about 0.3? The air comes and hits that surface, And if you consider one of them, you should take as stagnant, either the air is stagnant and the plane is moving fast, or if the plane is stagnant at that minute, air is coming and hitting it, but it comes to a stop at the nose because the stagnation point, that's the pitot tube, like, when it is facing the stream of. All right, if you decide that is also wrong, yeah, we can't use it, but it is better than the other one, isn't it? All right. Okay. Any other question? Only one of them is moving. The air is still, the plane is moving. And so if you take if you're sitting in the plane and assuming the air is coming on to you, at one, it is moving with that velocity. And then at two, it comes and hits the nose and stops there. That's what it is. Or solve it the other way around, no problem. Okay. Interesting. While traveling on a dirt road, the bottom of a car hits a sharp rock and a small hole develops at the bottom of its gas tank. If the height of the gasoline in the tank is 30 centimeters, determine the initial velocity of the gasoline at the hole. Discuss how the velocity will change with time and how the flow will be affected if the lid of the tank is closed tightly. So it is just say if that is the tank of gasoline, and if this is the gasoline inside, and you are creating a small hole here for whatever reason, and then the gasoline starts leaking out like this. We will take this point as 1 on the surface and the outlet as 2, and we will apply the Bernoulli equation in this form: P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V1 squared V2 squared over 2g plus Z2. And the height difference between these two is given as 30 centimeters, so which will become 0.30 meters.